very good afternoon to all. I welcome you all for the first year and first semester B.Sc. My name is Dr. Arjun. I will be handling physical chemistry. So, before getting into the topic, slightly I will be discussing about the course program. Some of you are in the different combination B.Sc le PCM ತಗೊಂಡಿದ್ದೀರಾ CBZ ತಗೊಂಡಿದ್ದೀರಾ. You are into different combinations. And from there, if you, for example, if you take it as CBZ, the paper will be chemistry, botany, zoology paper. ನಿಮ್ಮ exam ಬರಿತಾ ಇರ್ತೀರಾ plus 2 languages and one the Indian Constitution you will be writing. So in that, if you come into the chemistry paper, chemistry le ಎಷ್ಟು you will be writing for 80 marks theory. Theory will be for 80 marks and internals 20 marks irutte. So total it will be for 100 marks. 100 marks ಅಲ್ಲಿ 80 marks theory. In that 80 marks theory, the chemistry will be divided into 3 different parts. ಯಾವ್ದು? Organic chemistry, inorganic chemistry and physical chemistry. From the each unit part, there will be around 25 to 26 marks divide ಆಗಿರುತ್ತೆ ಕ್ವಶನ್ ಪೇಪರ್ ಅಲ್ಲಿ 80 marks ಕ್ವಶನ್ ಪೇಪರ್ ಅಲ್ಲಿ from the each part there will be the marks distribution of 26 to 27 marks. This is the distribution of marks out for the each part of the chemistry. So today I will be discussing in the physical chemistry, that is unit 7, where before getting into the topic we should be knowing what is physical chemistry. It is the study of macroscopic and microscopic phenomena in chemical systems in terms of motion, energy, force, time, thermodynamics and quantum chemistry. These terms we are going to study with physical relationships. So especially with macroscopic and microscopic systems. So coming into the unit 7, there we are going to discuss with respect to law of corresponding state. These are the objectives of this unit. So in this unit we are going to study about law of corresponding state, reduced equation state, liquefaction of gases. What is liquefaction of gases? ಏನು ಹಂಗಂದ್ರೆ it is the conversion of gas into liquid form. So that is the liquefaction of gases. Also we are going to discuss the principle underlying liquefaction of gases, how it works, how it is liquefied form, and also there is a Joule-Thomson effect, Joule-Thomson experiment for the liquefaction of gas, and Joule-Thomson effect in isoentropic process, and Joule-Thomson coefficient, inversion temperature, and van der Waals constant. So here also we will be discussing about critical temperature and critical pressure. So this unit basically with respect to liquefaction of gases, and there are 3 different types of liquefaction. We'll get into that. So what is introduction? Introduction, liquefaction. What is liquefaction? Liquefaction is the transformation of gaseous substance into liquid state. We are going to convert gaseous substance into liquid state. For example, hydrogen, ಈಗ CNG ನೋಡಿದಿರಲ್ಲ, compressed natural gas, it will be in the cylinder in the liquid form. So when it is left to the environment, it will be converted into gas. So how they will be converting into gas into liquid form andaga, under the high pressure and temperature they will be converting. So that principle we will be studying in this unit. So that is the concept. And the change in Outcome of change in physical condition like temperature, pressure, and volume. How it varies when it is converted into gas into liquid form. I hope it is audible, Allah. Yes or no? Yeah, okay, fine. So here we are going to study Joule-Thomson effect. In this, Thomson Andrew was the first person to study the change in state from gas to liquid. So in the carbon dioxide, he studied that relationship how to convert gas to liquid form. So essential conditions for liquefaction of gas andre the study of critical temperature, critical pressure, critical volume, and their relationship. So, critical temperature andre the temperature at which it is converting from one point to another means from gas state to liquid state. One temperature iruttala at certain temperature, so that temperature will be denoted as critical temperature. And critical pressure andre the pressure needed to convert the gas into liquid state. So that will be critical pressure and critical volume, where if you convert the liquid will be having more when it is left to gas. So the changes in the volume also takes place when converting from gas to liquid. So that is with respect to critical temperature, critical pressure, and critical volume. Here, the gaseous system is transferred into liquid state. There is a tremendous decrease in the volume. So when it is left to gas, the volume increases. When it is pressurized and kept in under certain condition, the volume of that same, whether whatever hydrogen, nitrogen, whatever the gases you are taking, it will be in the less volume liquidally. So this decreases in volume can be effectively brought about lowering temperature by increasing the pressure. So this is with respect to introduction and coming to law of corresponding state. What does this corresponding states here? If two or more substance have same reduced temperature and same reduced pressure, then they would have same reduced volume. So if the two or more substance, whether hydrogen, nitrogen, carbon dioxide, whichever the substance you are taking, which will be having same reduced temperature, which is taking ಅಷ್ಟೇ ಸೇಮ್ ಟೆಂಪರೇಚರ್ ತಗೋತಿದೆ ಕನ್ವರ್ಷನ್ಗೆ and same reduced pressure, same pressure it is taking to convert from one state to another state, that is from gaseous state to liquid state, then the same there will be the volume content in that will be same. So this is with respect to law of corresponding states. So what are the principles underlying under liquefaction of gas? The principles, the underlying for the liquefaction of gases are here the study of compression and expansion of gases in thermodynamic for the gas state is important to understand the liquefaction of gases. So the increase in pressure and lowering the temperature. The temperature should be kept lower. ಈಗ ನೈಟ್ರೋಜನ್ ಎಲ್ಲ ನೋಡಿರ್ತೀರಲ್ಲ it will be a very low less temperature when it is converted into liquid. So it will be acting like a coolant in the fridge, refrigerator also. So that will be in the liquefied form. So that will be kept under high pressure and lower temperature. So when high pressure is applied to gas, it gets compressed. When the temperature is lowered, it gas gets cooled. So and it is converted into liquid. These are the principles underlying in. And whatever the critical temperature, the temperature above which gas converted into liquid. That is known as critical temperature. And critical pressure andre the minimum pressure necessary to liquefy the gas. Means gas is converted into liquid state. So that is the minimum pressure required. That is known as critical pressure. These are the basic terms you should be knowing. Critical temperature andre ಏನು, critical pressure andre ಏನು, liquefaction of gases. So liquefaction of gases can be done by three different methods. That is by cooling alone, and by applying pressure and cooling, and by Joule-Thomson effect. Liquefaction of gases andre the gas can be converted into liquid by three different types. So one can be done, or some of the materials can be by cooling itself, it can be converted into liquid, and some other needs pressure with cooling. Cooling ಮಾಡ್ತಾ gas state na cool ಜೊತೆಗೆ pressure, if you bring it out, you can convert it into liquid form. And one more method is Joule-Thomson effect. These are the three different types of liquefaction of gases. So first two methods you will be knowing. By cooling directly it can be done, and by applying pressure and cooling it can be converted into liquefaction. What is Joule-Thomson effect? That we are going to study in this unit. So Joule-Thomson effect andre when the gas expand initially, the internal work is done by the gas, overcoming the intermolecular force of attraction at expense and energy. This phenomena is known as Joule-Thomson effect. Here, it's nothing when a gas under high pressure is permitted to expand adiabatically into a region of lower pressure. The temperature falls. This is due to when the gas expands suddenly. So if you come to the experimental part, you will be going to know here the Joule-Thomson experiment, which is in the thermally insulated system. These are the thermally insulated tubes that are thermally insulated walls or tubes. So here the one substance, that is gas, we are going to send where the input, this is the input, where this is the output of that, where you are going to convert the gas into liquid form. The gas which is in the inlet, here the pressure will be P1 and V1. So this is the nothing but the porous plug. Porous and there will be certain ratio where it can pass from A part to B part. So here that is the porous plug. We are going to insert it in between the wall. So when the gas is inserted, where with respect to pressure and volume get constant, even the temperature is kept constant T1, that is denoted by T1 temperature. So when it passes to the porous plug under high pressure, the gas is converted into lower form. So here we can see the change in pressure and volume also with respect to temperature. These changes can be measured using Joule-Thomson experiment. So here the this experiment consists of thermally insulated tube. These are the thermally insulated tube, and a porous plug is placed inside the center. The porous plug is placed inside the center, that can be seen here, and the tube is filled with a gas at two different pressure. So such as pressure when it passes to the porous plate, the pressure will be changed to P2 on the other side of the porous. Here the gas at constant pressure and volume is allowed inside through inlet, and there will be the gas changes. Adiabatic expansion will take place inside the insulated wall. So the change in the gas pressure, volume, and temperature, it can be noted down. So here the net work done means ಈಗ gas, the state of the gas is changing from gas to liquid or high pressure gas to low pressure gas. The state of the gas is changing. So here we are going to calculate the work done. So what is the net work done? Work done ಹೆಂಗ್ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತೀರಾ? The final output minus the initial what you are given. So whatever for now, ಈಗ the amount of A is converted into B ಅಂದಾಗ whatever the time ಆಗಲಿ ಅಥವಾ whatever the product form of the percentage of the product how we are going to calculate ಅಂದಾಗ B minus A. ಬಿ ಟೋಟಲ್ ಅಲ್ವಾ ರಿಯಾಕ್ಟ್ ಪ್ರಾಡಕ್ಟ್ ಫಾರ್ಮ್ ಬಿ ಮೈನಸ್ ಎ ಮಾಡಿದಾಗ ವಾಟ್ ಎವರ್ ದ ಚೇಂಜಸ್ ಟೇಕಿಂಗ್ ಪ್ಲೇಸ್ ಫ್ರಮ್ ಎ ಟು ಬಿ ವಿ ಕ್ಯಾನ್ ಕ್ಯಾಲ್ಕುಲೇಟ್. ಸೇಮ್ ಫಾರ್ ದಿಸ್ ಆಲ್ಸೋ ವಿ ಆರ್ ಗೋಯಿಂಗ್ ಟು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಪಿ ಟು ವಿ ಟು ಟಿ ಟು ವಾಟ್ ಎವರ್ ದ ಔಟ್ಪುಟ್ ಮೈನಸ್ ಇನ್ಪುಟ್ಸ್ that are input what we are given, so that we can calculate the work done. Work done ge this is what we are going to calculate the work done for the Joule-Thomson effect. So W is denoted as work, and how we are going to calculate P2 V2 minus P1 V1. That is the pressure in the state 2 and volume in the state 2 minus pressure in the initial state, that is P1 V1. That you are going to subtract, you will get W is equal to P2 V2 minus P1 V1. So from thermodynamic first law of thermodynamic what it says andre delta E is equal to Q plus Q plus W. ಅದು ಇದು Q ಇಲ್ಲ ಇಲ್ಲಿ, you cancel, ಅದು typing error ಇದೆ. Delta E is equal to Q plus W. So delta E is nothing but change in internal energy. So whatever the changes taking place inside the system. Q is the small q ಇದೆಯಲ್ಲ, Q it refers the quantity of energy supplied to the system, whatever the energy supplied to the system, and W is the work done by the system. DW ಇದೆಯಲ್ಲ, that is the work done by the system. So that is from first law of thermodynamics. Delta E is equal to Q plus delta W. So in the next, Q is equal to, since the condition is in adiabatic, Q is equal to 0. Adiabatic andre the transfer of heat to surroundings. There will be no transfer of heat to surroundings, so Q will be 0. Surroundings andre ಇನ್ನೇನಿಲ್ಲ, transfer of heat to surroundings andre this is a system. For example, this wall insulated wall, this one you will take it as an system, and with respect to surroundings andre with respect to room temperature, that is denoted as this is the system. With respect to room, if we keep it in a room, we are going to note it as a surrounding. So if the variation in the temperature between the system and the surrounding, ಈ ಸಿಸ್ಟಮ್ ಟೆಂಪರೇಚರು ಮತ್ತೆ ಸರೌಂಡಿಂಗ್ ಟೆಂಪರೇಚರು ಸೇಮ್ ಇದೆಯಾ ಅಥವಾ ಚೇಂಜಸ್ ಆಗ್ತಿದ್ಯಾ, ವೆದರ್ ಇಟ್ ಈಸ್ ಗೆಟಿಂಗ್ ಇನ್ಫ್ಲೂಯೆನ್ಸ್ಡ್ ಆಫ್ ಇಟ್. ಸೊ ದಟ್ ವಿ ಆರ್ ಗೋಯಿಂಗ್ ಟು ನೋಟ್ ಇಟ್ ಡೌನ್ ಹಿಯರ್. ಸೊ ಅಡಿಬ್ಯಾಟಿಕ್, ದಟ್ ಈಸ್ ವಾಟ್ ದ ಕ್ಯೂ is equal to 0. Adiabatic ಅಂದ್ರೆ the transfer of heat to surroundings. There will be no heat transfer between the system and the surrounding. So that's why the Q will be 0. And delta E, if you insert this Q is equal to 0 in the equation 11, what will happen? Delta E is equal to W. Really note it down. This in this line Q illa idu. In the equation 1, delta E is equal to Q plus W. So where E2 minus E1, that is the state from E2 minus, that is the E2 minus E1. That is nothing but E2 andre E2 and E1 are nothing but internal energy of the gas before and after expansion. So E2 and E1, the here it will be written as E1, and in the second step that will be denoted by E2. E2 minus E1, that is the equation 2, which can be written as minus of P2 V1 V2 minus P1 V1, so that we can calculate internal energy of the gas also, whatever the changes taking place. The energy also changes agatala when it kept in the certain pressure. The energy can be liberated or consumed by that gas. So that also we can be calculated. E2 minus E1 is equal to minus P2 V2 of minus P1 V1. That is the equation 2. So we get by resolving E2 plus P2 V2 minus E1 plus P1 V1. So that is in the equation 3 here. And E is enthalpy. E andre enthalpy. So enthalpy, it is the sum of internal energy and pressure with respect to pressure, time, volume. So internal energy of the gas before and after expansion. So H is equal to E plus PV. See, this is nothing but law of conservation. So whether the energy is conserved by the system or not, that can be calculated using the equation H is equal to E plus PV. That is the equation of law of conservation, energy conservation. So H2 is equal to H1 or H2 is equal to minus H1. If you take it on left hand side, it will become minus H2 minus H1 is equal to 0, or delta H is equal to 0. Therefore, if Joule-Thomson expansion delta H is equal to 0, Joule-Thomson expansion occurs at constant enthalpy. Means constant enthalpy andre the internal energy of the gas before and after expansion is constant. So if delta H is 0 andre it is in the constant. If it is in the positive andre there is a cooling effect is observed during the expansion. So when the gas is expanded, the cooling can be seen when the value is in the negative. When delta H is positive, means delta H calculate ಮಾಡಿದಾಗ positive value ಬಂದ್ರೆ the heating effect is observed from that expansion. So when the gas is expanded, the delta H enthalpy ಏನಾರು 0 ಬಂದ್ರೆ it is in the equilibrium or it is in the temperature is in the constant. Whether delta H is positive, we can see cooling effect. Positive bandre, we can see cooling effect, the values of delta H, and delta H which is in negative, we can see heating effect in the system. So this is what the calculation of delta H using Joule-Thomson principle. So next is the Joule-Thomson coefficient. So here the coefficient is defined as rate of change of temperature with pressure at constant enthalpy. The enthalpy is kept constant. The what rates the rate of change of temperature with pressure can be seen. So with different substances will be having different rate of conversion from gas to liquid. So at what rate the substance is converting, we can be calculated using those Joule-Thomson coefficient. Here mu is equal to T by P with constant H. So T is the temperature, P is the pressure, H is the enthalpy of the system. Enthalpy we ಇಲ್ಲಿ bracket ಅಲ್ಲಿ small numerator ಬಂದರೆ H where H is where H will be constant. So H will be constant andre the constant is enthalpy. H is denoted as enthalpy which is kept constant. The it will be in constant where varying temperature and pressure. So T by P bracket of H constant means enthalpy is kept constant. If the mu here also, if the mu is in positive, the cooling effect is observed during the expansion. Means the coefficient is positive, the cooling effect is observed during the expansion. Means expansion of gas andre from gas to liquid convert agಬೇಕಾದ್ರೆ we can see the cooling effect. If the mu is in negative, the value which comes calculating the negative heating effect is observed during the expansion. So this can be seen. And when mu is in 0, there will be no heating or cooling of the temperature. So that can be known as inversion point. Mu ಏನಾದ್ರು 0 ಬಂದ್ರೆ temperature by pressure calculate ಮಾಡಿದಾಗ when there will be denoted as inversion point means there will be no heating or cooling of the temperature is observed. So this is with respect to Joule-Thomson coefficient. And next is with respect to inversion temperature. ಈಗ inversion temperature ಅಂದ್ರೆ ಹೇಳಿದ್ದೀನಲ್ಲ. So what is inversion temperature? The temperature at which Joule-Thomson coefficient changes its sign is known as inversion temperature from positive to negative or negative to positive. So where will be sudden changes. So that can be noted as mu is equal to 0 there, which can be noted as inversion point. So this is inversion temperature, the temperature at which the coefficient changes sign is known as inversion temperature. So the temperature below which the gas expands adiabatically into a region of lower pressure, cooling effect is observed. When the gas is expand adiabatically into region of lower pressure, you can observe the cooling effect. So if gas undergoes adiabatically expansion above this temperature, heating effect is observed. So there is a critical temperature Also, where change in conversion of gas to liquid that can be at the temperature can be denoted as critical temperature. So here they are given some of the examples here. Hydrogen, helium have very low inversion temperature. That is 193 Kelvin. So 193 Kelvin andre it will be around minus 80 degree Celsius. So hydrogen and helium they have to be converted into liquid andre it should be kept at the temperature of minus 80 degree at certain pressure. So then only the hydrogen or helium it can be converted from gas to liquid. Liquid state ಗೆ ತಗೊಂಡ್ಬರ್ಬೇಕು ಅಂದ್ರೆ minus 80 degree Celsius ಅಲ್ಲಿ maintain ಮಾಡಬೇಕು temperature. And also with respect to helium ಗೆ that is 33 Kelvin respectively means minus 240 degree Celsius ಅಲ್ಲಿ ಇರಬೇಕು helium ನ if you want to convert gas to liquid state. So here inversion temperature is related to van der Waals constant that can be denoted as T1 is equal to 2A by RB. So Ti is nothing but inversion temperature ಅಷ್ಟೇ. That is if you are knowing the expression Ti ಅಂದ್ರೆ ಏನು ಅಂದ್ರೆ inversion temperature. So that is enough from this. Inversion temperature ಅಂದ್ರೆ it's nothing but the change in coefficient of the sign. So coefficient change ಅಂದ್ರೆ ಏನು? The rate of change of temperature with pressure. The rate at what the temperature and pressure at constant enthalpy. So while you're taking the gas, for example, ಇಲ್ಲೇ ಇದೆ ನೋಡಿ example. For hydrogen, it needs around 193 Kelvin at certain pressure. If you are changing from one state to another state, that is from gaseous state to liquid state, that is the temperature at which it can be denoted. So this temperature is the inversion temperature. Minus 80 degree another inversion temperature for hydrogen. Minus 70 degree andro it is not a inversion from changing of state. ಈಗ minus 70 degree ಅಲ್ಲಿ ಇದ್ರೂ it will be in the gaseous state. When it comes to minus 80 degree, it will convert into liquid state. So that temperature is known as inversion temperature. And derivation for reduced equation state. So it is the critical constant where given critical temperature andre critical pressure andre you should be knowing that is a basic terms. Critical temperature where it is converted from one state to another state by that is denoted as critical temperature. Critical pressure the minimum that pressure required to convert from one state to another state. So here the van der Waals equation that is can be denoted by B is equal to P is gas constant, A is the gas constant of A. So here they are given for A and B. So R is the universal gas constant. So substituting the values in van der Waals equation, we get P plus A by V square. That is V into V minus B is equal to RT. RT is the van der Waals equation. So R is the universal gas constant, T is the temperature, V is the here V is nothing but molar volume. So the molar number of moles in a volume. So P is with respect to pressure and C is the constant. So next P is equal to we are going to substitute the equation that is B, A and are in this given van der Waals equation. Van der Waals equation really we are going to substitute this. This is the van der Waals equation. We are going to substitute these values. We will get the equation P plus 3pc by vc square divided by v square into v minus vc by 3. So that is 8 by 3 to pc vc by temperature into T constant. So dividing the above equation Pc and pressure constant and volume constant on both the side, we will get the equation this while dividing pressure and volume kept constant. So next the equation after substituting we will get the equation 1. In the next we can denote the P by Pc. These whole terms can be replaced. P by PC, VC by V, V by VC. These two terms can be written in this. P is equal to PC that can be denoted by PR. V by VC that can be denoted as written as VR, and T by TC that can be denoted by TR, where PR, VR, and TR are reduced pressure, volume, and temperature. So these are nothing but reduce pressure, reduce volume, and reduce temperature from the equation 1. So therefore the one equation can be written in the here as it is 8 by 3 T by TC ಅಂತ ಇದೆಲ್ಲ for example ಇಲ್ಲಿ it can be T by TC can be replaced by TR. So 8 by 3R you can see here. So hello, yes. The equation 2 is known as van der Waals reduced equation state. So this is the reduced form of van der Waals equation. And here general equation applicable to all the substances, and it is made based on the value of reduced pressure, reduced volume, and temperature, which is known as law of principle or corresponding state. So what does the law of principle or corresponding state means? It is the same when two or more substances have the same reduced temperature and same reduced pressure. For example, hydrogen and helium, which is having, for example, I'm telling you, which will be having same reduced temperature and same reduced pressure, then the reduced volume also will be same. So that is the law of corresponding state. So here, same the expression for van der Waals which we have derived, that is for reduce pressure, reduce volume, and reduce temperature. When the pressure and temperature are reduced, if there is a same value, then the volume, reduced volume also will be of the same. That can be derived from the van der Waals reduced equation state. So this is the derivation. And next, this is the end of the first unit. Where liquefaction of gases. This unit is mainly of liquefaction of gases. There are three different types: by liquid, by reducing temperature, by pressure and reduce temperature, and by Joule-Thomson. So in that we are going to study critical temperature, critical pressure, and inversion temperature, and van der Waals equation for reduced temperature, reduced volume, and reduced in temperature. When the pressure and temperature reduced, the volume automatically the volume also gets reduced. So when converting gas to liquid form. So in the next unit, that is indicators. Indicators ಅಂದ್ರೆ ಏನು? So indicators are mainly used to determine the end point of the reaction. So ಈಗ ಒಂದು reaction ಹಾಕಿರ್ತೀರಾ. So you need to determine the end point, whether the reaction is completed or not. So that we can be determined by adding indicators. So indicators are the chemical substance which indicates the equivalence point or chemical reaction by changing its color from one color to another. Then we can identify whether the reaction is completed or not. So indicators are mainly used to determine the end of this reaction. So next, uh, in this indicators in this unit 8, that is theory of indicators, we are going to study what are indicators and the types of indicator. That is definition types, uh, acid base indicator, redox, adsorption indicator, and examples for each type, and theory of indicators. Here, no, two important theories are there: Ostward's and Quirinite theory, and indicator constant. Also, the action of phenolphthalein and methyl orange in acid base solution. So, we are going to discuss the pH titration curve for strong acid versus strong base, weak acid versus strong base, and weak base versus strong acid. So, depending on these different reactions, we are going to choose different indicators depending on the reaction. So choice of indicator in these types of titration. We are going to choose the indicator on the types of titration and color change and their pH range. So different there are many number of indicators where need to be having different pH range, and the color changes. It changes the color depending on their chemical substance. The color will be changed, and also there is a universal indicator and their definition. So what are indicators? And the indicators are chemical substance which indicates the equivalence point or end point of the reaction of a chemical reaction by changing its color with in certain pH range. So there will be a pH range for different indicators. One indicator in the ಇನ್ನೊಂದು indicator ಗೆ the pH range will be different depending on the chemical substance present. So for example, phenolphthalein, methyl orange, methyl red, diphenyl amine. These are the indicators. So what are the characteristics and what the indicators are going to do? Andre indicators are display different colors in acidic and alkaline solution. Next, methyl orange, um, phenolphthalein indicator, and bromocresol green. So those are the structures of indicators. And next is the theory of indicators. Here, theory of indicators andre there are two theories of indicators, that is Ostward's theory and Quirinite theory. The acid-base indicators occurs in two termers form that changes one form to another form. from acidic media to basic media, the form of the structure of that indicator changes. So that was explained by Quinoid. So that theory is known as Quinoid theory. So coming to first theory, that is Ostwald's theory. So in this theory, the acid base indicator is either weak acid or weak base. The acid or base that will be of weak, that only partially dissociate or partially ionize in the solution. When you add indicators to the solution, only the partially ionization taking place in the given solution. So those may be weak because of weak acid or weak base, that my indicator. So here an acid base indicator is weak organic acid. So that can be denoted by H N I N. So or weak organic acid or weak organic base. Base के OH. How you are going to denote? Base के you are going to take OH. Acid के it can be denoted by H plus H. So here we are going to denote HLIN. So that can be denoted weak organic acid. So dissociates to give H plus plus IN minus. H is the acid and IN is the organic complex. Ionized indicator. So this will be denoted as unionized indicator. This is the ionized indicator. So what is the andre unionized indicator andre? There will be no dispersion taking place. Ionized indicators are giving positive and negative charge by gaining or losing electrons. This would be knowing ionized indicators andre gaining positive or negative charge by gaining or losing electrons. Ionized indicators. So the unionized indicators have has color different from ionized indicators. So they'll be having color difference. The color of indicator depends on the relative proportion of unionized indicator molecule and its ions. So why the color difference? You can see, you can ask any sir color difference between the acidic and basic. Andre, when it is the reaction in the indicator getting ionized because of relative proportion of unionized indicators and its ions. So where there will be no equal uh, what you can say dispersion of the ions taking place because of unionized indicator andre whether gaining of positive or negative charge by gaining or losing electron. So depending on the electrons, the ionization taking place. The equation of this can be written as K, that is nothing but K rate constant. Ion is the complex organic group. Ion can be written as complex indicator constant. The K-ion is the rate constant or indicator constant. So the reaction rate to constant. K is equal to IN H plus IN minus by H IN. So H IN is nothing but weak organic acids. If the indicator solution is in acidic, it has excess H plus ions. So these points are very much important. If the indicator solution in acidic mediaದಲ್ಲಿ indicator ಆಗ್ತಾಗ it has excess of H plus ions. When it is shifted to equilibrium on left hand side, the indicator remain unionized. When it is changes to left hand side Hn plus, there will be unionized form. This color of the solution will be in the A. So if the indicator solution is in the base, Then the hydroxide ions or OH minus ions of the base combines with H plus ions to form water. H plus OH minus ions when it get combines the neutralization, that is the H2O, the formation of indicate to form H2O. So from this point you can understand the whole concept. If the indicator solution is in base OH minus hydroxide ions of a base combines with H plus ions to form H2O. H2O ಅಂದ್ರೆ water. So here water will be in the neutralization alwa. H plus ಅಂದ್ರೆ that will be in the acidic media and OH will be in the basic media. When the H plus get neutralized added to OH, the neutralization of taking place, the forming water. So next is the action of phenolphthalein indicator in acid-base titration according to Ostwald's theory. So here we are going to discuss keeping phenolphthalein as the weak acid. Phenolphthalein is a weak acid, dissociates to give H plus plus pH minus. So it dissociates to give H plus plus pH minus. The rate constant or indicator rate constant can be written as KIN is equal to H plus pH minus. That is the product divided by reactant H plus H pH. So pH is nothing but complex organic group or organic substance. KPH is the indicator constant or rate constant. So this is left hand side ಏನಿದೆ, this is unionized form and this on the right hand side, this is ionized. Ionized form ಅಂದ್ರೆ gaining positive or negative charge by losing an electron or gaining of an electron. So in acid solution, equilibrium shift towards the left. In the basic solution, the equilibrium shift towards the right. This is in the basic media, this is in the acidic media. And the solution have pink color in basic ions. And the H plus ions form indicator to form water. So same with respect to phenolphthalein indicator. Next is methyl orange. So methyl orange is a weak base and it dissociate to give Me plus OH minus. So here the dissociation. So methyl orange indicator rate constant can be written as KIN is equal to Me plus into OH minus divided by Me methyl OH. So here the product by reactant that can be written. So a basic form andre that will be in the methyl orange, that will be in the yellow color. Yellow color andre unionized form. This is the unionized form. This is the ionized form. Ionized form andre that will be in the acidic form, which is in red color. So in basic media, indicator is unionized form. Therefore, the color is in the yellow. Where in the acidic media, the ion increases. It gives red color the solution. So OH ions of the indicator react with H plus ions to form water. So everything should be getting neutralized. So forming water. So this is with respect to Ostwald's theory. Ostwald's theory explain. Ostwald's theory, it explains the acid-base indicator is either a weak acid or weak base that only partially ionizes in the solution. So that is with respect to Schwartz theory. Next is quinonide theory. So in this theory, the acid base indicators occurs in two tautomers form. That is change from one form to another form. So tautomers are nothing but a structure isomers of chemical compound that are readily instant. So isomers andre ಏನು? Which is having same chemical formula with different structures. So that can be represented as benzoinide and quinonide form in the quinonide theory. So there are two different forms. One form which is exist in acidic solution, that is, and other form which is in the basic media or alkaline solution. Also change in pH causes transition between these two forms. One form in the another form, the structure variation can be seen. The indicator in the acidic media, the structure will be of different, and when it is in the basic media, the structure of that will vary. You can see with some of the examples. These are the example for strong acid and strong bases. Should be knowing. Hydrobromic acid, acid, nitric acid, sulfuric acid, or acid, strong acid. So strong bases, yeah, should be knowing. And next example, this is benzoate form and quinonide form. Uh, Here phenolphthalein exits in benzoate form in acidic media. So this is the structure of phenolphthalein, that is C20H14O4. Phenolphthalein is an indicator. So in acidic media, that will be in the benzoate form, in the quinonide form, in the basic media. So even in the structure, it varies. You can see in the structure, C double bond ethyl is C, dissociate to this C O, where adding of OH gives C double bond. So this can be seen in acidic and basic media differences of the indicator. And second example, they are given with methyl orangery indicator. By adding OH minus, the structure of N group. This is the structure where N double bond N. So by addition of OH minus, by reduction of H plus, it gives NH. So this is the structure of methyl orange. That can be in acidic media, it can be in quinonide form. In basic media, it can be denoted as benzoate form. So next is the action of phenolphthalein indicator in acid-base titration according to Schwartz theory. Schwartz theory, how the acid-base indicator acts for phenolphthalein indicator. Phenolphthalein is a weak acid. So the rate constant previously we have discussed, K in is equal to, this is the reactant by, sorry, this is the product by reactant. So that is from the equation. This is the product form divided by reactant. So H plus into pH minus divided by HPH. And next is the choices of indicators. How you are going to choose the indicator on the type of the reaction with different titrations, whether reaction ಅಂದ್ರು ಆಗುತ್ತೆ, titrations ಅಂದ್ರು ಅಷ್ಟೇ, acid base, strong acid versus strong base, weak acid versus strong base. So different forms ಇರುತ್ತಲ್ಲ. So depending on different titration, we are going to choose different pH range. ಆ pH range different ಇದ್ದಾಗ we are going to see the indicator, choice of indicators. So we are going to choose of that indicator. Indicators na ಹಿಂಗ್ choose ಮಾಡ್ತೀರಾ. Different reactions ಇದ್ದಾಗ different pH ranges ಹೋಗುತ್ತೆ. So depending on the pH ranges, we are going to choose the indicators by the reverse manner. So the suitable indicators for the pH titration has to following these characteristics. It should be show these characteristics. So the color of pH corresponding to endpoint of the chemical reaction, indicating the reaction is completed. So there should be sharp color change at the end point of the reaction. Means end point of the reaction only indicator color it should change sudden. Means it and the contrast color change should be easily distinguished. Means the properties depending on the pH of the solution at the end point. When the strong acid is treated against a strong base, vice versa, the solution is neutral pH. Neutral andre pH will be at the 7 end point. So therefore, indicators having sharp color within the pH range of 4 to 10 can be used for this reaction. Strong acid versus strong base reaction ತಗೊಂಡಾಗ it should be range of pH range will be 4 to 10 because the neutralization point ಎಷ್ಟಿದೆ 7 ಅಲ್ವಾ. So 4 to 10 ಆಗುತ್ತೆ ಅಥವಾ 6 to 8 whatever the pH range, we should change that indicators we are going to use. ಆ ರೇಂಜ್ ಅಲ್ಲಿರೋ pH indicators ನ ಯೂಸ್ ಮಾಡ್ತೀವಿ. So in the transition of weak acid and strong base, the pH endpoint will be 7. So any indicators color between pH 8 to 10 can be used. For weak acid, andre it will be around pH 5 to 6, and the strong base andre the pH will be around 13 to 14. Strong base though scale ಹೇಳಿದ್ನಲ್ಲ, ನ್ಯೂಟ್ರಲೈಸೇಷನ್ 7, ಈ ಕಡೆ 3, ಈ ಕಡೆ 14. Strong base andre it will be around 14. Strong acid andre it will be around 3 to 5, and near to 7 whatever the acids present, this will be weak acid. This side above 7, 8 to 10, that will be in the weak base. This will be strong acid and strong base. So here strong weak acid versus strong base andre the weak acid will be the pH of 3 and the strong base will be around pH of 14. So the point of neutralization is same for 7, but we are going to choose the indicator which is around sharp change agbekkala, because there is a lot of consumption of base, means OH plus ions will be consumed to neutralize this acid, weak acid alva. So to getting this neutralized, there should be sharp changes. So we are going to use the pH of 8 to 10. Next topic is pH titration of strong acid versus strong base. Strong acid ಯಾವ್ದು ತಗೊಂತೀರಾ? That's why you should be knowing the examples. A table column ಹಾಕಿದಿನಲ್ಲ, should be knowing what are the, you should make down the point. Strong acid ಯಾವುದು, weak acids ಯಾವುದು, strong base ಯಾವುದು, weak base ಯಾವುದು ಅಂತ. For strong acid, here we are going to take hydrochloric acid, and strong base ಗೆ we are going to take sodium hydroxide. So ಇದ್ರದ್ದು pH ಎಷ್ಟಿರುತ್ತೆ hydrochloric acid the pH will be around 3. So sodium hydroxide the pH will be around 14. That is why it is known as strong base. Here the reaction is taking place versus strong acid versus strong base. So the point of neutralization is 7. You can see it from the plot. Plot al ಕಾಣಿಸ್ತಿದ್ಯಾ? You can see the point of neutralization, that is 7. Whenever if you add the volume, whether with respect to ಬೇಸ್ ಬೇಸ್ ಆರು ಹಿಂಗೆ ಆ್ಯಡ್ ಮಾಡಿ, ಇಲ್ಲ ಹಿಂಗೆ ಆಸಿಡ್ ಆರು ಆ್ಯಡ್ ಮಾಡಿ. The point of neutralization will be 7. So this is the plot of it. Exactly it is shown because ಏನಕ್ಕೆ ಅಂದ್ರೆ strong acid versus strong base ಅಲ್ವಾ. When you are going to add strong base sodium hydroxide, ಇದು in the beaker will take it hydrochloric acid, that is strong acid. ಎಷ್ಟು ವಾಲ್ಯೂಮ್ if you going to add to this beaker in pH 7 ಗೆ ಎಷ್ಟು ನ್ಯೂಟ್ರಲೈಸ್ ಆಗುತ್ತೆ, that is what they are given in the plot. The equivalence, the number of volume added or volume of moles added to the given solution. So here the curve pH titration is for strong acid versus strong base. The vertical andre, that is what the pH of this plot is for strong base where the pH is around 14, and this plot is for strong acid. The pH is starting from 1. The point of neutralization is 7. So whenever you are going to add strong acid versus strong base, this is the plot what we are going to get. And for this strong acid versus strong base, methyl orange, phenolphthalein can be used as an indicator. This is the pH titration for strong acid versus strong base. Next, you can see the pH titration for weak acid versus strong base. Weak acid ಗೆ ಯಾವ್ದು ತಗೊಂಡಿದ್ದೀವಿ ಇಲ್ಲಿ? Acetic acid ತಗೊಂಡಿದ್ದೀವಿ. CH3COOH and sodium hydroxide. That is the strong base. Weak acid ಗೆ acidic acid ತಗೊಂಡಿದ್ದೀವಿ. So weak acid it is starting from 4, 2.3 to 4, and strong base it is from 14. You can see the difference between the plot in the previous go idukku. How elaborated plot it is getting from the strong acid versus strong base. Idralli hinge it is getting shortened up. So ಏನಕ್ಕೆ it is having weak acid. Weak acid ಗೆ it doesn't consume more strong base. For example, weak acid, here it is taken acidic acid ತಗೊಂಡಿದ್ದೀವಿ. In the beaker, we are going to take strong base. The pH will be around 14. In the burette, beaker ಅಲ್ಲಿ ಇರೋದು pH around 4 ಇದೆ. ಈ pH 4 ಇರೋದು 7 ಆಗೋದಕ್ಕೆ it doesn't consume more base or more sodium hydroxide. So whatever ಅರ್ಥ ಆಗ್ತಿದ್ಯಾ? beaker ಅಲ್ಲಿ ಇರೋದು the pH will be around 4. 4 ಇರೋದು 7 ಆಗೋದಕ್ಕೆ ಎಷ್ಟು? The point of neutralization, that is 7. ನ್ಯೂಟ್ರಲೈಸೇಷನ್ ಪಾಯಿಂಟ್ 7ಗೆ ನ್ಯೂಟ್ರಲೈಸ್ ಆಗೋದಕ್ಕೆ ಎಷ್ಟು ಬೇಕು ವಾಲ್ಯೂಮ್ ಬೇಸ್ ಆಡ್ ಮಾಡ್ತೀರಾ? ವೆರಿ ಲೆಸ್ ಅಲ್ವಾ? ಸೋಡಿಯಂ ಹೈಡ್ರಾಕ್ಸೈಡ್ ವಾಟ್ ಯು ಆರ್ ಗೋಯಿಂಗ್ ಟು ಆಡ್, ದಟ್ ವಿಲ್ ಬಿ ವೆರಿ less quantity. So that we are going to get it from the plot here. That is the weak acid versus strong base. See, for simple you need to know andre scale. This is 7. Weak acid andre it will be around 4 to 5. And strong base andre it will be around 14. So this weak acid to neutralize ಎಷ್ಟು ಬೇಕಾಗುತ್ತೆ? The quantity it's very less ಅಲ್ಲ. So to neutralize this, the quantity of base added to this acidic solution will be very less. ಈ ಬೇಸ್ ಸ್ಟ್ರಾಂಗ್ ಬೇಸ್ ಇದೆಯಲ್ಲ, ಇದನ್ನ ಒಂದ್ ಸ್ವಲ್ಪ ಇದಕ್ಕೆ ಆಡ್ ಮಾಡಿದ್ರೆ ಆಸಿಡ್ಗೆ ಇಟ್ ವಿಲ್ ಗೆಟ್ ನ್ಯೂಟ್ರಲೈಸ್. ಮೀನ್ಸ್ OH ions ಆಡ್ ಮಾಡಿದ್ರೆ it will get neutralized and form water molecule. So acid is an H plus alva, OH minus add ಮಾಡಿದ್ರೆ it will get neutralized and form water. So that is the plot from the weak acid versus strong base. Next is the pH titration of strong acid versus weak base. So here weak base, it is in the pH value of 8 to 10. So strong acid though, it will be around 2 to 3 HCl though. So strong acid, hydrochloric acid, they are taken. For the weak base, they are taken sodium carbonate. That is the expression they are given. So this is from the plot. A plot between pH of solution and amount of acid or base added to it. It can be denoted. Same as this is for strong acid versus weak base alva. If you measure in the scale, this is 7. Strong acid andre, it will be around 2 to 3. So what is the weak base andre? Weak base will be around 8 to 10. 14 alla. 14 idre, that will be a strong base. Weak base andre, it will be around 8 to 10. So the amount of acid adding to ಬೇಸ್ ಈ ಬೇಸು 8 ಇದೆಯಲ್ಲ, 7 ಆಗೋದಕ್ಕೆ ಎಷ್ಟು ಬೇಕು, ಎಷ್ಟು H ಪ್ಲಸ್ ಅಯಾನ್ಸ್ ಆಗಬೇಕು, ವೆರಿ ಲೆಸ್ ಅಲ್ಲ. ಸೊ ಇಫ್ ಯು ಆಡ್ ವೆರಿ ಲೆಸ್ ಆಸಿಡ್ ಟು ದಿಸ್ ಬೇಸ್, ಇಟ್ ವಿಲ್ ಗೆಟ್ ನ್ಯೂಟ್ರಲೈಸ್. OH ಗೆ H ಪ್ಲಸ್ ವೆರಿ ಲೆಸ್ ಆಡ್ ಮಾಡಿದಾಗ ಇಟ್ ವಿಲ್ ಗೆಟ್ ನ್ಯೂಟ್ರಲೈಸ್ ಅಂಡ್ ಫಾರ್ಮ್ ವಾಟರ್. ಸೊ ದಟ್ ಈಸ್ ವಾಟ್ ದೇ ಎಕ್ಸ್ಪ್ಲೈನ್ ಫ್ರಮ್ ದಿಸ್ ಪ್ಲಾಟ್, ವೇರ್ the plot between pH of solution and the amount of acid or base added to it. So this is the titration curve we get. And next is the universal indicators. Next topic is the universal indicators. Universal indicator is a mixture of many indicators. So it is a mixture of many indicators which give different colors at different pH value. So it will be having different mixtures of indicator. Means different indicators will be mixed together. So that can be denoted as universal mixture. Different pH ಅಲ್ಲಿ different colors ಕೊಡ್ತಾ ಹೋಗುತ್ತೆ. So for example, methyl orange ತಗೊಂಡಿದ್ವಿ, around 3 it will be showing red. Around 7 ಅಲ್ಲಿ it will be in the 7 ಅಲ್ಲ, around 8 ಅಲ್ಲಿ it will be in the yellow color. So different pH, the methyl orange indicator is showing different color alla. So mixture of different indicators. If you add methyl orange plus phenolphthalein, one more indicators, different pH ಅಲ್ಲಿ 3L ಒಂದು color, 4L ಒಂದು, 5L ಒಂದು, it will be different indicators will be present in that alla universal indicator ಅಂದಾಗ. So at different pH it shows different color. So different color ಅಂದ್ರೆ different endpoint. 7 ಬಂದಾಗ ನ್ಯೂಟ್ರಲೈಸೇಷನ್ ಒಂದು ಕಲರು, ಆಮೇಲೆ 8 ಬಂದಾಗ ವೀಕ್ ಬೇಸ್, ದಟ್ ವಿಲ್ ಬಿ ಹ್ಯಾವಿಂಗ್ ಒನ್ ಮೋರ್ ಕಲರ್ ದಟ್ ಕ್ಯಾನ್ ಬಿ ಡಿನೋಟೆಡ್. ಸೊ ಮಿಕ್ಸ್ಚರ್ ಆಫ್ ಮಿಥೈಲ್ ರೆಡ್, ಮಿಥೈಲ್ ಆರೆಂಜ್, ಬ್ರೋಮೋ, ಥೈಲ್ blue, phenolphthalein, it covers the overall pH range from 3 to 11, what I have explained here. So that is the example they are given. Mixture of 3 or 4 indicators, mixture of methyl red, methyl orange, bromo, thiol, blue, phenolphthalein. It covers the range of pH from 3 to 11. All the pH range will be covered by these indicators, the mixture. So that is what known as universal indicators. And next is the types of indicators. Types of indicators and the acid base indicator, natural acid base indicator, indicators for oxidation and reduction, adsorption indicator, chemical indicators, chemical moisture indicator, chemical indicators for sterilization. So depending on the structures and characteristics, they will be having different indicators. So that plot we can see here having different indicators and their pH. It can be seen here, whatever the pH range and types of indicators. So methyl violet, methyl green, all the different types of indicators are seen in the x-axis and the pH range, where it will be having one pH range, the color changes, one some of them will be having two until the pH 12, there will be changing colors. We can be having different indicators. So whatever the point we need to identify the reaction, we can use according to their pH value. The indicators can be chosen on their pH. Also, next is the characteristics of chemical indicators or indicators. While you choose an indicator, it should have means some of the characteristics. So what are the characteristics here means it must not react with the substance or should have pure chemically form. ಅಂದ್ರೆ whatever the solution you are taking ಅದ್ರ ಜೊತೆ ಮಿಕ್ಸ್ ಆಗಬಾರ್ದು. Don't get confused. ನಾನು ಹೇಳಿದಷ್ಟು you get into it. That's enough. Here in the first characteristics, it must not dissolve in an indicator. For indicator ಆಗ್ತಾಗ it should not dissolve inside the other substance. So indicator should act as a substance, but it should not dissolve with another substance. And it must not degrade in the whole reaction. So should not indicator should not degrade. So as the reaction proceeds, the indicator should not degrade. That is one more character. And when the reaction reaches the equilibrium point, end of the indicator must have noticeable colorization. Means the change in color should be seen while the end of the reaction or while change of pH. The reaction. These are the characters, main characteristics of indicators. It should be having. It should not dissolve. It should not degradable, and end of the reaction, the color changes will be seen. So degree of physical integrity may not alter by making it thicker. So whatever it should not, and also it should not affect the rate of reaction. When adding the indicator, indicator should not act as a catalyst. Catalyst agi indicators act ಮಾಡಬಾರ್ದು. So these should be the characteristics for using of indicators. So this is the end of the unit. Today I have completed 2 units. ಏನಾದ್ರು ಡೌಟ್ ಇದೆಯಾ? ಈಗ ಕೇಳಿ ಈಗ ಡೌಟ್ಸ್ ಇದ್ರೆ.